In part 6 of the Unit 6 notes, we are going to be covering the structure of covalent compounds. When two elements with similar electronegativity bond, typically nonmetals, electron sharing will occur. This process helps each atom to reach a stable octet. Hydrogen is an exception which only requires 2 electrons to be stable. When hydrogen has 2 electrons, it is similar to helium, which is the closest noble gas to it. We can show this process using Lewis dot diagrams. Pairs of shared electrons are circled to show that they are a part of a bond, whereas a non-bonding pair of lone electrons are not circled. It is important to note that the total number of electrons cannot change in a chemical reaction. Electrons can only be moved between atoms and rearranged in order to achieve an octet. This goes back to our law of conservation of mass. In our example shown below, we have a nitrogen atom which has 5 valence electrons. It's going to be bonding to 3 hydrogens which each have 1. We've color-coded the dots here just to make it a little bit easier to see how everything is coming together. When these atoms come together, we're going to have shared electrons in between each of the atoms. So this nitrogen and this hydrogen are going to be sharing these 2 electrons here. That means that these electrons exist within the radius of both atoms simultaneously. Think of a Venn diagram. Because of this nitrogen atom went from having 5 electrons to now having 8. It has a stable octet. And each one of the 3 hydrogens now has 2, which is all it needs to be satisfied. For our first checkpoint, we are going to be drawing Lewis dot diagrams for these 2 covalent compounds. We're going to start off with a carbon atom. And for a carbon atom, I'm going to draw the electrons as X's, since it isn't quite so easy to change the color within the program while recording. For each of my bromines, I'm going to have 4 of them. They're going to have 7 dots around them. Now, in an ionic compound, we would have transferred these electrons from the carbon to each one of the bromines, but this time we're going to be sharing the electrons instead. So I'm going to rewrite this with carbon in the middle, with its 4 valence electrons. And each place where there's an empty space next to that electron is kind of like a little docking port, where each one of these bromines can come in and bond. So I'm going to put 1 bromine on the top. It's going to come in with its 7 valence electrons, and on the side where there's just 1, it is going to bond with the one from carbon. And we're going to do that for each of the 4 sides. Now, while it isn't completely necessary to use different symbols like I'm using here, the X's and the dots, this will hopefully make it a little bit easier for you to see that 1 electron in each bond is coming from one atom and the other electron is coming from another. It'll also be a little bit easier when we get to more complicated structures. In our second example, we have a phosphorus atom, and this one is going to have 5 valence electrons. So again, I'll use X's to represent that. Then I have 3 fluorines, and each one of these fluorines is going to have 7 dots. When they all come together, we're going to put our phosphorus in the middle with its 5 valence electrons. And it looks like I have 3 docking ports here, which is good because I have 3 atoms that want to come in and bond. So I'm going to bring a fluorine in on each of those sides. I'm going to circle any of those shared electrons. Now I have my final structure. Now, looking at the structure, we could also say a few things about it. The phosphorus has 3 bonds. It also has 1 lone pair of electrons, whereas each of the fluorine atoms has a single bond, and it has 3 lone pairs of electrons. For our second question, we were asked how we could determine that these 2 compounds contain covalent bonds using the formulas provided. Each of the formulas consists entirely of nonmetals. And there's one more important part that we want to add to this, and there are no polyatomic ions. You might remember from one of our previous videos that there are instances where you can have covalent bonding where there are all nonmetals, but you would have to have a polyatomic ion in order for that to occur. Some molecules are not able to satisfy the octet rule by making only single covalent bonds between the atoms. A double covalent bond is a covalent bond formed by atoms that share two pairs of electrons. In this example, we have two carbon atoms that are going to bond together along with four hydrogen atoms. Now we would start with a single bond between each. So carbon would have a single bond to the other carbon, and then single bonds to each of these two hydrogens. But when it does that, it doesn't have enough electrons. It needs to make an additional connection with the other carbon across from it, so it makes a second bond. Now if we count each of our bonds, which have 2 electrons each, we would have 2, 4, 6, 8 electrons around the carbon on the left. And with the double bond on the right, we have 2, 4, 6, 8 for the carbon on the right as well. It is only possible for these two carbon atoms to form an octet if you have that double bond. You could also potentially have a triple covalent bond. A triple covalent bond is formed by atoms that share 3 pairs of electrons. In this example, we have 2 nitrogen atoms bonding together. You would start with an initial connection between them. But if I started with a single bond here, I would have 2, 4, 5, 6 electrons, not an octet. So you would take 1 electron from each, put them into the middle, and then you would share an additional set of electrons. That would get you up to 7. You'd have to do it one more time in order to get to that octet. And you can see the finished product here. So we end up with 3 electrons in the bond from the nitrogen on the right, and 3 electrons in the bond from the nitrogen on the left. So each nitrogen has 3 bonding pairs and a single lone pair. Each of the covalent bonds that we have looked at so far have involved each of the atoms that are bonding contributing one of the electrons to the shared pair. A coordinate covalent bond is an alternate type of covalent bond, in which one of the atoms provides both of the electrons in the shared pair. In order to see this, we're going to be looking at carbon monoxide, which is CO. Now initially, when these two atoms are going to come together, they could form a connection right here with a single bond. When this is done, the oxygen on the right is going to have access to 2, 4, 6, 7 valence electrons. Carbon is going to have access to 2, 3, 4, 5. Neither one is satisfied yet. So you take 1 electron from each and put it into the center. So this electron could go here, this one can go here, and then they would bond, which would result in 8 electrons for the oxygen, but only 7 for the carbon. In that instance, if you try to share another one from each, you would end up with too many electrons on oxygen while having enough on carbon. So there's another way of doing that. You can take both electrons from an oxygen and put both of them into the bond. And you can see that finished product here. So we have 2 bonds where you have 1 electron contributed from each of the atoms. And then a third bond where both electrons came from a single atom, the oxygen here. So when one atom contributes both electrons, that is called a coordinate covalent bond. In our next checkpoint question, we are going to be drawing a Lewis dot diagram for oxygen, O2. We're going to start off with an atom which has 6 valence electrons. Our second oxygen is also going to have 6 valence electrons. We're going to start with a single connection between them. And when I do that, the oxygen on the left has access to 2, 4, 6, 7, and the oxygen on the right has access to 2, 4, 6, 7. Neither one is satisfied yet. So I'm going to take an additional electron from either side and put them into the middle. And I'm going to redraw this off to the side. So we have an oxygen and an oxygen. And now there are 2 bonds between them. Now each oxygen would have 2468, 2468. So both of them are following the octet rule. Our second question is asking for the type of bond which is required. This is not a coordinate covalent bond because each one is contributing one electron into each of the bonds. This is going to, however, be a double bond. There are also exceptions to the octet rule. One such exception is an incomplete octet. In some compounds, atoms are stable with less than 8 electrons surrounding the central atom, especially smaller ones. So here we have a beryllium atom. It starts off with 2 valence electrons. It can share electrons with hydrogen, and by doing so, it ends up with 4 in its outer shell. Based on the octet rule, this shouldn't be stable, but this compound does exist. You can also have compounds which have an odd number of electrons. There are a number of molecules whose total number of valence electrons is an odd number. It is not possible for all of the atoms to follow the octet rule, yet these molecules still exist and are stable. Examples of this are NO2 and O2Cl. You could also potentially have something called an expanded octet. Atoms of the third period and beyond are capable of exceeding the octet rule by having more than 8 electrons around the central atom. Starting with the third period, the d suborbital or sublevel becomes available, so it is possible to use these orbitals for bonding. If you were to look at this phosphorus atom in the middle, each one of these lines represents 2 electrons, or what we've been drawing, 2 dots which are then circled. If you count it up, this phosphorus has 2, 4, 6, 8, 10 electrons around it, so 2 too many. And the sulfur over here has 2, 4, 6, 8, 10, 12. So, based on the octet rule, these molecules should not exist, but they are able to. For this unit, you should know that what types of exceptions to the octet rule could occur: incomplete, odd electron molecules, and expanded octet, but you are not going to be expected to draw them. We're going to look at these in more detail in our next unit on VSEPR and molecular shapes. That concludes Part 6 of the Unit 6 notes. When we come back for Part 7, we are going to be comparing polar and nonpolar bonds and looking at the properties of covalent compounds.